Have you ever paused to truly consider how incredible it is that we as humans consistently manage to understand each other?
It really is something, isn't it?
I mean, language is this wild, intricate system, often full of arbitrary connections between sounds and meanings, and yet somehow we communicate. We coordinate, build entire societies. It almost feels like magic.
Yeah, it does.
But that magic brings up a fundamental puzzle.
Yeah.
How do communities actually establish these shared communication systems in the first place? Is it through some grand conscious agreement, or is there something, more organic at play?
That's right. And for a long time, the prevailing idea was that successful communication relied on a kind of shared, universal understanding, what we call common knowledge, or maybe very deliberate strategic reasoning among people.
Right.
But what if the truth is much simpler? What if our complex language systems emerge from countless local, everyday interactions, almost, without us realizing it?
That's the core mystery we're diving into today. We're going to unpack a really groundbreaking 2004 cognitive science paper by Dale J. Barr. It's titled Establishing Conventional Communication Systems. Is Common Knowledge Necessary? And we'll explore how his ingenious use of multi-agent computer simulations shed new light on this very question.
Yeah, so today our mission is really to explore how simple, self-focused, or you could say egocentric interactions between individuals can actually build the incredibly sophisticated linguistic systems we use every single day.
And challenge some long-held assumptions.
Exactly, challenging some very long-held assumptions about human communication.
Okay, so to really get Barr's work, we first need to look at the theory he was challenging, this common knowledge view.
Right.
This idea largely stems from David Lewis's influential theory from 1969. He suggested that conventions like, driving on a certain side of the road or using particular words evolve from recurring coordination problems.
Think of it like game theory, yeah, like the work of Thomas Schelling. People need to align their actions, but there might be multiple ways to do it. The choice itself can feel arbitrary.
So the key idea here is that these coordination problems involve interdependent decision-making. You want to align your actions with someone else, but the specific action might not inherently matter, just that you both pick the same one.
Right. So individuals, or agents, as they're often called in these theories, reason strategically. They base their choices on mutual expectations.
Mutual expectations, okay.
And Lewis argued that these patterns become conventional through the accumulation of common knowledge. If something is common knowledge, let's say solution S works for problem P in community C, then when any two members, A and B, meet, they can mutually expect each other to stick to S.
And it's not just that I know it, but I know you know.
Exactly. And I know that you know that I know it.
Yeah.
It goes on infinitely. Theoretically, that's the common part.
Okay, so where does this common knowledge actually come from, especially for language?
Well, the source was often seen as communicative interaction itself. The idea was by interacting with a broad enough sample of your community, you could sort of generalize that knowledge to the whole group.
Makes sense.
Lewis actually put it quite nicely. He said something like, if one has often encountered cases in which coordination was achieved by conforming to a certain regularity and rarely or never encountered cases in which it was not, he is entitled to expect his neighbors to have had the same experience.
So you assume others have seen the same patterns you have?
Pretty much. And what's fascinating here is how profoundly influential this theory became for understanding language use.
Wow.
Researchers like Herb Clark, building on work from the early 80s and into the 90s, really applied this framework.
Right, I remember Clark's work on common ground.
Exactly, common ground. He argued that this shared understanding, this common ground, and the deeper common knowledge are absolutely crucial for successful communication. Like, knowing what someone means by the movie playing at the Roxy depends on both of you having this shared, mutually understood context.
Okay, that seems logical. It feels intuitive. But then, this elegant theory started running into some, unexpected real-world challenges.
Precisely. There's a growing body of empirical evidence that suggests we don't always reliably consult common knowledge in our everyday conversations.
How so?
Think about when you're talking to someone and you refer to the book, maybe assuming they know exactly which book you mean, even if you just finished reading it and they've never seen it.
Right, I do that. We all do that sometimes.
That's a little egocentric bias, isn't it? Studies by researchers like Horton and Keyser and his colleagues back in the early 2000s actually showed this experimentally. Listeners often considered objects not known to the speaker.
Even when it was clear the speaker couldn't know about them.
Yeah, even when there was clear evidence the speaker was ignorant or had a false belief about something. This tendency to kind of default to your own perspective directly violates the assumption that we consistently check what's mutually known before speaking or interpreting. So this creates a significant paradox, right? If successful communication relies on these deep representations of mutual knowledge, and yet we, as language users, don't consistently use them.
Then how does anything work?
Exactly. How is it possible that we don't constantly misunderstand one another? It really forces us to ask, why aren't people constantly talking past each other?
So given these challenges, what was Barr's radical idea? How could language possibly emerge without this foundational shared understanding?
His core proposal is, well, pretty bold. Common knowledge is simply not necessary for conventions to emerge.
Not necessary at all.
Not necessary. Instead, he suggests that our shared meanings are semantic representations that get coordinated through use. It's a byproduct, he says, of individual attempts at coordination among speakers and listeners, which are distributed over time and across the language community.
So it's less about everyone knowing the same thing globally and more about lots of little local interactions just working things out.
Exactly, it's emergent. And this idea wasn't entirely out of the blue. There was earlier work hinting at this. Like what? Well, Peyton Young in the 90s showed that social feedback, just seeing if something worked or not, could substitute for having deep knowledge. Conventions could emerge even with incomplete information or choices that seemed, less than perfectly rational.
Okay.
And Shoham and Tenenholtz in 97 used computer simulations not for language, but for other social conventions, showing they could emerge without common knowledge.
But what's really cool is that studies of actual human conversations have kind of observed this happening, right?
Absolutely. Researchers like Garrett and Anderson, way back in 87, watched pairs of people working on a maze task together.
Oh yeah, the map task.
That kind of thing. They naturally developed temporary, shared ways of talking about locations. They invented their own little mini conventions just between the two of them.
Just for that task.
Right. And even more strikingly, Garrett and Doherty in 94 found these local conventions could even generalize to a larger virtual community, even when the participants didn't explicitly know they were part of this bigger group. This really suggests conventions can bubble up from these individual dyadic episodes, just two people talking, rather than needing some kind of global top-down awareness.
Okay, so if you want to study how this happens across big groups and over time, you can't easily stick thousands of people in a lab.
Exactly. It's incredibly difficult, and that's precisely why multi-agent computer simulation is such a powerful tool here. It allowed Barr to model these community-level patterns as emergent products of individual agents interacting.
And he could fiddle with the variables, right? Like population size, how they interact.
Precisely. See what factors are really crucial for building these shared systems.
And his simulation approach was a bit different from other ways people modeled language evolution.
Yeah, somewhat. For instance, you have these multi-generational models where language changes over, generations as new agents learn from older ones.
Right, like how grammar might slowly shift.
Exactly. They're great for those slow structural changes, but maybe less suited for really rapid lexical innovations. How fast new words like website or Riz pop up and spread.
Okay, and what about other emergence through use models?
There were earlier ones, like from Luke Steele's and others. They showed how conventions could arise from individual communicative acts. They often use analogies like bird flocking.
Ah, where the flock moves together without a leader, just birds adjusting to their neighbors.
Exactly that. Complex, coordinated behavior from simple local rules. But some of those earlier models, while compelling, sometimes assumed agents had maybe lots of direct interaction or even unlimited memory.
Which could kind of sneak global knowledge back in.
In a way, yes. It might imply agents knew more about the whole system than Barr thought was necessary. So Barr's study really aimed to zero in on that. What's the absolute minimum knowledge agents need? Can coordinated communication happen even if individuals know very, very little about the bigger picture?
Okay, so let's get into the simulation itself. What was the basic setup? The signaling game.
Right. So imagine a simulated population of agents. Each agent has a lexicon, basically, a mental map connecting, say, 4 different meanings to 4 different forms or words.
Okay, simple vocabulary.
Very simple. And this map works both ways for producing signals, like speaking, and for comprehending them, like listening.
And then the goal was?
The goal was for the entire population to converge, to end up using the same meaning-to-form map. But crucially, this target map wasn't pre-programmed. It had to emerge organically from their interactions.
How did they learn?
Agents updated their internal maps based on simple reinforcement signals. Basically, did the interaction work? Success. Or did it fail? Failure signal. And they only got this feedback from the specific partner they just interacted with.
And who talked to whom?
Just random pairings. Dyads formed stochastically pure chance encounters.
Okay, and they tested different ways the agents could learn from these encounters.
Yeah, two main learning approaches or regimes. First was reinforcement learning, or RL. You can think of this as kind of brain-like.
Neural networks.
Sort of, yeah. Connections in the agent's mental map got stronger if communication worked, weaker if it failed. It's a continuous, cumulative process, subtly adjusting over time.
Okay, and the second one?
The second was stay switch, SS. Much simpler, more rule-based. If a communication strategy worked, the agent stayed with it. If it failed, they swapped out the failed mapping for the least reliable one they had stored in their limited memory.
Ah, so memory size was key here.
Exactly. This regime let the researchers directly control and quantify how much social information an agent had by just varying its memory size. These SS agents were also designed to be conservative, trying to keep clear one-to-one mappings, like how we generally don't like having too many perfect synonyms.
Right, avoids ambiguity. So they manipulated the learning type, memory size, population size, and also the community structure, you said.
Yes, those were the key variables they tweaked.
So first up, unstructured populations. Anyone can talk to anyone, pure random mixing. What happened?
Well, the reinforcement learning RL model was pretty impressive right off the bat.
Yeah.
All populations converged. Every single run ended with a shared communication system. Even the really big ones, 10,000 agents.
Wow, and quick.
Remarkably quickly. A single system emerged after surprisingly few interactions per agent, even in those huge populations. Each agent only talked to a tiny fraction, maybe 2%, of all possible partners.
So they didn't need to know everyone.
Not at all. This was a huge finding. Convergence can happen with very partial knowledge where direct interaction with everyone is impossible.
And how did the new language spread?
It showed that classic S-curve. Slow start, then a rapid takeoff, then leveling off as everyone adopts it. That critical mass effect.
Which people used to think needed complex strategy.
Exactly. But here, it just emerged from these simple local reinforcement interactions. No grand plan needed.
Okay, but what about the other model, the simpler stay switch?
Now that gave a really counterintuitive result in these unstructured settings.
Go on.
In the smaller populations, like 100 agents, convergence was actually most efficient, fastest, when agents had tiny memories, like remembering just the last two interactions was optimal.
Wait, less memory was better.
Yes. For these simple agents in this setup, trying to remember too much about past interactions actually hindered coordination.
That seems backwards? Why?
Well, Barr's explanation is like trying to shoot at a moving target. If the system, the convention, is changing rapidly as it emerges, older information quickly becomes useless, even misleading.
So focusing on what just happened is better than relying on potentially outdated info.
Exactly. Trying to use too much global knowledge, which might be out of date, actually impaired coordination at the community level. It's a real less is more situation sometimes.
And did stay switch work in the big unstructured populations?
Generally, no. It struggled and often failed to converge in the larger populations of 500, 1,000, or 10,000 when interactions were purely random. It highlighted the limitations of that simple strategy in a totally mixed environment.
So that less is more finding, especially for stay switch in smaller groups.
Mm.
It really challenges our intuition about knowledge, doesn't it? What's the big takeaway?
It strongly suggests that sometimes simple, locally focused rules can be more effective for establishing coordination, especially when things are dynamic and changing. It forces you to reconsider if more information or more global awareness is always the best route. Sometimes, maybe not.
Okay, fascinating.
Yeah.
But real societies aren't usually completely random mixing bowls. What happens when you add structure? When interactions are shaped by social geography?
Right. This is where it gets even closer to reality. In the second set of simulations, they put the agents on a 2D grid, like a virtual space.
And agents talk to their neighbors more.
Exactly.
Yeah.
Interaction probability was highest with close neighbors and dropped off with distance. It simulated having local neighborhoods or clusters.
And how did the learning models fare here?
Well, now the stay switch SS model dramatically improved, especially for large populations like 1,000 agents.
Oh, really? The opposite of the unstructured case.
Right. Optimal convergence happened at a specific neighborhood size around 9 agents interacting locally. Suddenly, this simple strategy worked much better when interactions were focused within smaller, more stable groups.
So repeated interaction within a local group helps build that critical mass needed for the simpler strategy to take hold.
That seems to be the implication. Even if the whole population is huge, having that stable local interaction structure makes a big difference for the state switch agents.
And what about the brain-like reinforcement learning model?
Interestingly, it showed the opposite trend again. For RL, convergence was actually worst at the smallest neighborhood sizes and best when agents could interact more broadly across the grid.
Huh. So RL benefits from more diverse interactions, while SS benefits from local stability.
It seems so. The RL agents, perhaps because they learn continuously, might need that broader input to sort of average out local quirks and find the best global solution.
But the most exciting thing here was the dialects, right?
Oh, absolutely. Even when the whole community didn't settle on one single system, which happens sometimes, especially with smaller neighborhoods.
They didn't just fail.
No, they often self-organized into distinct, spatially organized dialects. Different regions of the grid would converge on different but internally consistent communication systems.
Like little linguistic pockets.
Exactly. And the number and size of these dialects depended on the neighborhood size. Smaller neighborhoods tended to lead to more smaller, distinct dialects.
Were there patterns to where they formed?
Yes, agents near the corners of the grid, for instance, tended to form more stable dialects. They were kind of shielded from influences from multiple directions, and neighboring dialects, while different, often showed similarities. They weren't completely alien to each other.
So even without one global language, you still got high local coordination.
Precisely. Coordination within the community remained high because of these localized similarities. And importantly, this happened within a single generation of agents.
Unlike other models where dialects took generations to evolve.
Right. Here, it was purely an effect of the interaction structure and the learning dynamics within one simulated lifespan.
It really is like the digital version of regional accents or slang popping up.
Yeah.
You travel somewhere else in the same country, and they just have their own way of saying things, but it clearly arose from the same basic need to communicate locally. It's amazing it emerges so naturally from these simple rules.
It really is. And the overall conclusion from these simulations is pretty clear. They strongly support this emergence through use view.
That common knowledge isn't the driving force.
Right. Large populations of essentially egocentric agents just focus on their own success. Not modeling others' minds can establish and sustain conventional communication systems without needing common knowledge.
They didn't even know they were in a community, did they?
Nope. They lacked any concept of community and were, as Barr put it, indifferent to the identity of their conversational partners. Didn't matter who they talked to, just whether the interaction worked. Yet, convergence or stable dialects were highly likely outcomes. So the key thing is they lack that meta-knowledge, knowledge about what others know.
Exactly. They don't have common knowledge in that deep, recursive sense. They just respond to what's immediately salient, what works in the current interaction. This really challenges Lewis's idea that you need common knowledge to override mere salience. These simulations suggest simple salience, driven by reinforcement, can be enough when interactions are distributed effectively.
So bringing this all together, what are the bigger implications for us, for human communication? Well, it offers a powerful alternative explanation for why we manage to communicate so well most of the time, even though psychological studies show we do often act egocentrically.
We think from our own perspective first.
Right. But maybe that's okay, because the commonality, the shared understanding, doesn't necessarily require everyone to constantly compute mutual knowledge. It can emerge organically as a byproduct of all those individual attempts to connect.
The shared system arises from the bottom up.
Precisely. Now, this raises an important point. Saying common knowledge isn't necessary for conventions to emerge doesn't mean humans don't have it or use it.
Good point.
We clearly can reason about what others know. We can learn about the patterns in our communities and use that knowledge strategically. But Barr's work suggests maybe that ability, maybe even the feeling of being in a community with shared understanding, is a consequence of participating in these emergent shared practices rather than a strict precondition for them ever getting started.
So the practice might come first, and the awareness follows.
That's a really interesting possibility opened up by this work.
And the paper pointed towards future research too, right? Combining different models.
Yeah, definitely. Thinking about how to combine multi-generational models good for slow grammatical change with these emergence through use models, which seem better for rapid vocabulary shifts.
Like different mechanisms for different parts of language.
Potentially. And also integrating these agent models more tightly with psycholinguistics, making the simulated agents behave even more like real humans based on experimental data. Lots of exciting avenues.
So wrapping up, what's the final thought you'd leave us with from this deep dive?
I think the big picture here is a shift in perspective. Instead of maybe focusing so much on how ambiguous language can be and thinking we need these really complex cognitive fixes like deep common knowledge all the time,
We should appreciate the power of local
it's
interactions.
exactly. Appreciate how distributed, simple, local acts of coordination between individuals can naturally, almost automatically create the common ground, the shared representations that hold our language communities together.
It's quite profound when you think about it that way.
Oh,
Every small conversation, every time you try to figure out what someone means or make yourself understood, you're potentially playing a tiny part in shaping the very fabric of our shared language.
hmm
What new conventions are maybe emerging right now around you, just from people trying to connect and coordinate? Something to think about.
definitely.
Well, thank you for joining us on this fascinating deep dive into how language conventions might actually emerge.